Let me share. So this idea, what I'm going to talk about today, is a bit kind of workflow within like a PyMC ecosystem. So I'm going to show a bit of things that you already know about fitting a model, and then doing optimization with PyMC models, which is something we are doing quite a lot in the show. A notebook that I cleaned a bit today, but I shared some time on this course on this thread that was open January 2023, PyMC for Bayesian optimization, where someone was just asking a way too broad question, has anyone used PyMC for Bayesian optimization? And then Christian, very helpful, said, look at this Thomas old blog post, which I think is like a couple of years old. Yeah, 2019. So this is kind of the state of the art of the documentation, how to do optimization in this ecosystem. And some people have been, I think, finding this issue because it has a very good title, and they're just looking for Bayesian optimization PyMC. Probably they find this. So someone was interested in something slightly different, which is this kind of optimization on uncertainty, where you're asking what data should I collect to get the most expected gain. That's something that's very common in the discussed in the literature with GPs. And before I go to the example that I'm going to talk about, I just wanted to mention that he came back and he shared a notebook that seems to be really cool, not only because it starts with an MIT license copied on the top of the notebook, but it seems to have done some funky stuff of doing like MCMC within optimization, or I don't know if it has a closed form updating where you can get the expected improvement of, I think, like probing a given X. I hadn't seen that in PyMC. So this seems very cool to look at, but I'm not going to talk about that. Instead, this other user, that can zoom a bit, said, I'm not interested in doing Bayesian optimization to optimize, parameters, or I think neither for deciding what should be the next data that I'm going to sample. What I got from what he said is he has a model like a black box neural network or something that he fits. And then, he gets a Bayesian neural network. And then at some point he wonders if he can like change the parameters to try to, approximate a given target. And how should those parameters be under some constraints? And specifically, it says, I would like to use a Bayesian neural network as a part of optimization loop. Let's say I can only change a selection of parameters in a given range. So there are hard constraints. What would be the optimal combination of parameter changes of my currently available, I guess, parameters to produce a given output plus some idea of the uncertainty on that output? As the Bayesian neural network is differentiable, this should be possible, but I haven't seen any examples that go into a similar direction beyond the black box. So I shared this notebook and I cleaned it today. So that was too much state of the art, but not enough. And I had to use actually the latest version of PyTensor. Otherwise, there were some things that were still broken. So you won't be able to run this unless you, basically install the latest version of PyTensor from the repo. But so I'm going to show the whole kind of workflow. You can go from like generative model to some inference to some optimization, just one way in a very specific setup. I can start. And I will show some things that maybe some folks are not familiar with in the code. So the most important is the best way to generate random seeds is to use a string, because that's much more fun than saying 42. And so you can do it with sum, map, or your string. Now, more importantly, the model is just a dumb linear regression where you have 5 features. You have some X input with 100 batch examples, get a mu, get a sigma, get a normal likelihood. So the first thing here is the pm.do, where that we are using this. I use this a lot when doing like basically testing if the model can recover parameters. So I define the generative model without any observed data. Then if I want to do the investigation for a given like values, you can use do. Let's say, let's fix the betas to these numbers, sigma to these. Then you call pmdo on the model, what you want to change. It's a new model, so you can just enter in the width context. And then, here I took a draw from y. I could have called sample prior predictive, would be the same thing. So we get a synthetic draw of y given these fixed parameters. Otherwise, you could just take a draw from the prior and the register or record which ones were actually drawn, which betas and sigma. But sometimes the parameters are too diffuse and you have to at least constrain a bit. In this case, sigma, for instance. Once you have the synthetic y, you can use PM observe on the same model, and you say, now I want to observe y to my synthetic draw of y. I'll call this my inference model, and I'm sampling. And then you can see in this case that with 100 draws, it recovered, not surprisingly, quite well. So -2, this should be -2, -1, 0, 1, 2, and sigma of 0.5. So that's just showing a workflow that was already mentioned some time ago. Yeah, pmdo, PM observe. Try to use it if you think it could be useful. Yeah. And then once the optimization part starts here, right? Once you have a model, you've learned some parameters, you might want to do something with what this model predicts. And you might want to work. So I don't know about, this is something I still have read very little. I don't know how to do optimization on stochastic variables. So I don't know how to optimize things on predictions of y. But it should be very straightforward to optimize things on expectation. So on the mean of y, for instance. So I'm grabbing, the ultimate goal will be, I grab the example, let's say that my goal is, once I learn this, find what is the x that gives me a y of 5, Something quite simple in this example, but maybe more complicated in a more realistic example. Can I find what code do I need to get that function that goes from x to mu? And then also give me the sample posterior predictive. So I'm going to show how to get sample posterior predictive without calling pm.sample posterior predictive. Because one, is not too hard, and second, it can be useful because sample posterior predictive has a lot of overhead and a lot of magic and also a lot of lack of control. And it might be useful to just know how to create those functions from a PyMC model. So the code, before I show what it does, looks like this. The first thing I do, I want to replace that mutable data x that had a shape of 100 by 5 by just a tensor, which is just an explicit input variable that has a shape of 5. So these will be the 5 features I want to input or to optimize to get a given y. I'm going to add a dummy batch dimension. This is something that if you have time, I'll come back. There's some commented code here that's for later. So let's say just an expand dimension. So it's a batch dimension, a dummy one by x. I'm going to call this function that I'll show the code later, which is posterior predictive function, where I pass a model, I pass my inference data, I say which variables I want to get. And I say I want you to replace x by this tensor or this tensor expanded, and is not specified here, but every variable other than y mu, well, mu was a deterministic, but any random variable otherwise is going to be replaced by the posterior draws from the trace. So I'm going to get a function where I put x and I get y and mu conditioned on that x and all the posterior draws from the trace, which is usually what you need when you want to do some optimization routines. I'm going to squeeze just that dummy batch dimension. I added to add just because in PyTensor you cannot just ask it to just throw away dimensions that existed from the beginning, but you can get rid of them by squeezing or also later by indexing. Okay. And then I'm just cleaning up and we get the graph. I'm not going to go over it, but basically we have that function, and I can show, for instance, testing with a dummy text value. I get the predicted mu from that function. I call eval, and I got something with a mean of 2.5, and indeed I got for change by 1,000 draws such values of mu. Okay. Once we have this variable, then we can make a cost function from it. So let's say we have a target, we want to approximate 5. I did a function. I don't know if this is the best function once you have all the draws from the posterior, or you should do something different. But I just did the difference of my targets and every predicted mean squared and summed them, and then compiled that into a cost function with PyTensor function x to cost. And for instance, if I try this x text, I get this very readable value of 24,000 into the cost. Okay. One thing that was mentioned in that issue is for many optimization routines, usually you want to use gradients. And obviously from PyMC and the PyTensor backend, we get those for free. So you can also just get the gradient function by doing ptgrad of your cost with respect to the variable you care about. And you get the gradient. Once you have that, you can pass that to any optimizer. So I just use the scipy minimize, pass the function, pass the gradient and the initial point, and it does it. And it finds the x's that minimize are these ones. And then the last step, because I separated, so I did, and this is what we are doing in Colgate at the moment. We are doing like optimization on the expectation. But then what you care about usually will be still like a posterior predictive over that state. So we can compile a second function from that other variable that was returned from the helper, which is predicted y, which is also a function of x, and all the other draws from the posterior. Just have to use compile PyMC to take care of the random seeding, but otherwise it's exactly the same as compiling a function. And then we can just get all the draws of posterior predictive by passing once result of x. And this is the result. So we got something close to 5, and we also get uncertainty, what this model would predict, even in your best case scenario. So before I go to the details, does the workflow make sense? Any remarks or questions?
Could you please elaborate on the function sample posterior predictive fan? Is it something you define in the notebook, or where does it come from?
Which function? This one?
The one that takes in no, above, where you replace something and sample from posterior.
You mean this function?
Yes.
Yeah, that's in this notebook. But in a sense, PM sample posterior predictive is doing a variation of this where it's not replacing, but it's creating a function that goes from a point to whatever variable you want to predict, usually y, and then just calls in a loop, giving all the draws from your inference data. This one is a bit different. This is creating the batched-like version of that, so there's no Python loop you need to do. So if you are doing autodiff, you also don't need to handle the gradients in a Python loop or something like that. Yeah. Okay, so I can show what the function is doing. So the function is basically using an old thing that exists in PyTensor, which is clone replace, which allows you to go to a graph and replace some nodes by some other variables, and something more new, which is the vectorized graph functionality, which allows you to, similar to NumPy vectorize or JAX, VMAP allows you to get PyTensor graph and say, I want to replace these by some variables by extended versions of those variables with like extra dimensions on the left, and then it just basically creates the correct graph where everything is expanded, which would get the same result if you call that function in a loop, basically. Plus broadcasting. Okay. So what we have to do is first create some dummy variables where we replace basically the model variables when you had, we're going to replace betas, sigma, which are the two unobserved variables, by some variable of the same type, so a scalar variable and a vector with size features. So I create this here in a dict, so it's just the model random variable, which you get from iterating through all the free random variables in your model. Is going to be replaced by a tensor with the same name and the shape we get from the inference data, and I'm skipping the chain and draw dimensions of the shape. Then I replace in the predicted variables is the one the user asked for, in our case, y and mu. So I get those from model var name. And I want those variables where I replaced the unobserved variables by the dummy posteriors and plus anything the user passed, in our case, that mutable x by the vector x. I clean a bit the graph, and there's something that would fail otherwise. And then and now we are ready to replace these dummy variables by the batch versions that have all the values for every chain and every draw. So create a new dictionary where the variables, which were the values of that dictionary, are now replaced by a constant, and it's just the values from the posterior. Okay, then you call PyTensorGraph replace vectorized graph, the variables you care about, and what you're going to replace in a way that should come out vectorized. And that's what returns this predicted y and predicted mu. Yeah. So this is not something it's something you could do easily. From your original model definition, you could just have written a function, obviously, that goes from x, betas mu to y. The reason I'm showing this is that it's, to a certain point, is model agnostic. And that's something useful in the project where we're just trying a bunch of different models. And then once we found a couple that we like, we want to do optimization with those. So in those models, basically, there are two deterministics that need to exist for us to do optimization. One is something called market share. The other is called total sales. And it doesn't really matter what's the model underneath. We can just basically extract those two deterministics, replace all the variables by the posterior, and provide an input variable that used to be something else in the model. And we don't need to care about how the model looked like. And that, I think, is quite handy and perhaps powerful. Yeah. Questions?
Yeah, do you still need I started reviewing that notebook, I skimmed it, but I didn't add the explanation text and review yet. Do you still need that or not? I didn't get to it yet.
Yeah.
Okay, cool.
Yeah.
I'll try to get to it when I'm done updating the stuff for this week's client meeting.
Yeah.
Yeah, I think that's really cool. I remember having to basically rewrite models so that I could do posterior optimization of some decision variables. So actually working with the models with the do operator and getting kind of replacing variables in the model itself seems pretty cool. So you don't have to duplicate the whole work, and then where you also then need to make sure that the model that you rewrote in NumPy later, that's actually the same model that you used for sampling and things like that. One thing I'm always a bit scared of with the whole do operator and stuff is that if something's wrong, I'd never know. So is there some way? So do you think that's kind of so how stable do you think that whole model replace stuff actually is? And do you have ideas about how that can be tested in a way that if I have a model, I can in some way verify that what I get back is what I want to get back?
Yeah. So for instance, in the Colgate, we are not right now getting any random variables, so we're just using mu. So one thing I do there is just, confirm the sanity check that at least there's no random variables in the return graph. So I just use the PyMC utility, assert no RVs. That's one thing. So there's the issue that can happen is when you replace variables that possibly depend on the variables you are replacing, which in this case wouldn't happen because you're just providing an input variable. That's the only cases where I've seen like this replace magic giving issues is, yeah, let's say you want to provide, you want to replace x by x, but then you have another function where y depends on the exponent of x, and you define that on the original one. So that's something we actually was a lot of work in that PM do. So we don't use this. We use something that has been developed for a while that exists only in PyMC, which is some top-of-sort replace thing that will look at your replacements and kind of put them in order in a way that it should do what you would expect it to do. But yeah, I just look at the graphs, and I did here, right? See if they look sensible. Test that actually, when I change things, it's working. But yeah, I've not been finding errors like silent errors, usually noisy errors of, I cannot rebuild this graph because there was a join operation and now that shape changed and it's just broken or something like that. But it leads to a point which is the safest way to do replacements is to not like this here where I did x none worked in this graph and I knew it would work because the way I defined it originally, it was like a mutable data and it assumed both dimensions were mutable. If it had been constant data, first I couldn't do that. Like PyTensor doesn't allow me to replace something with, something that was a matrix of 100 by 5 by something of 1 by 5. So in practice, the way this would work more generally would be you actually provide something that has the same shape as the original one, even though you only want to optimize over 5 values. So in this case, I broadcast. Now, everything is going to work fine in the sense that we use the Vectorized to add the batch dimensions from sampling. But now for optimization, I'm doing a lot of useless computation. Right, I'm doing a dot of 100 by 4000. So there's no utility in PyTensor right now to say unbatch a dimension. Except there is, which is you ask for a graph that is like you index the outputs. And then you tell it optimize when you compile, you ask it to optimize. And one of the things PyTensor does, but not very aggressively. And this is some of the stuff we added in. You ask for a graph that is like you index the outputs. And then you tell it optimize when you compile, you ask it to optimize. And one of the things PyTensor does, but not very aggressively. And this is some of the stuff we added in the project, which basically you tell PyTensor, I only care about, let's say, the last dimension. So ignore all the batch before that. And then PyTensor now has a chance to, from the graph that's valid, to just create the optimized graph that just doesn't have that dummy dimension you care about. So indexing is kind of an indirect way of getting rid of dimensions you don't care about. Now, it's not going to work great. Indeed, this dot still exists there, but they're in PyTensor that basically do things like lift the subtensor when it knows it's safe. So we're lifting it through drop dims, which is very easily. We're lifting it through softmax, things like that. So that we can do the safe replacement and then do the optimization to just don't do the computations I don't care about. Which maybe you would find even more scary. but those at least are like unit test the individual rewrites. Because we did not. So yeah, it's just kind of pushing this idea. You have a very general graph in a PyMC model, and then you want to do multiple things out of it. You want to take the log P2 sample. You want to, well, you even want to simulate data if you want to recover, like do parameter recovery studies. And you might also just grab those variables to do some optimization. So we just grab that graph and we partition it again in a different way.
Yeah, and I guess in a way that's something that the current architecture of PyMC lets us do, that Stan, for instance, or NumPy row or something just couldn't do in principle, I think, pretty much.
Yeah. So I remember in the one of the projects, we were using JAX a lot for the likelihood, and then you had to already write the functions in a way that you could reuse the code for them, like do the posterior predictive, so that you can grab the functions given some inputs are going to be useful. And this way kind of alleviates that. You just have to maybe mark it as a deterministic so we can find it in the graph. And we'll know this is what you want, and we replace the rest. Yeah. So you don't have to pre-partition your graph. Yeah, that was what I wanted to share. Yeah.
Yeah, it's definitely super cool. And I learned about that with the, it was really fun to see that, for sure. So thanks for writing this up, Ricardo. Now I'll test my understanding by trying to add descriptive texts, and we'll see how wrong I am.
Cool.
Where does that live? Can people grab that and play around with it?
Yeah, sure. I'll push it to a gist. Yeah. So I guess it's the lesson, or the lesson on the trying to sell our own or eat our own dog food is how much of NumPy can we get rid of? How much can we just stay with the PyMC model we defined? And this is just pushing that a bit more. I'll push the gist right now, yeah. But you'll have to wait for the next PyTensor PyMC release or install it from the Git repo. Because this required a PR that Jesse took a long time to review, and we could only get it merged recently. I don't know if he's even here, but I still will bash on him.
He's probably on the subway.
He said.
There you go. Landed. All right. Any other questions? Or this is the stuff, at least for me, the blog post that you and Tommy wrote, for example, like I think you went through it maybe in one of the Monday meetings, and I was like, oh yeah, sure, cool. But then I had to stare at that thing for a long time to actually sort of make it even begin to stick. So I think this is, at least for me, even just the sort of initializing these mostly empty models and then sort of doing and observing to sort of get the data in there and then crank out simulated data.
Yeah, right. Yeah, that's, I mean, the most common way you still see everyone is they write the data generating in NumPy, right? And then fit it into PyMC.
Yeah. Yeah. And that's not even sort of PyTensor magic. That's just what should be vanilla PyMC at this point,
yeah.
But that's new enough that old habits, etc.
I mean, that's immediacy of, I think, NumPy, where you see the numbers immediately. I think it really helps, right?
Yeah, but
It's
you know
a
what's
bit
cool
like,
about PyMC
you know,
is the coordinates.
Ex-
That's
Excel versus pandas data frames, right? Where you have the whole data there in your face.
yeah. I've definitely I fought the move to inference data like pretty hard when it was happening, and like now I'm like, when I see people sort of using shape, I'm like, what are you doing? Like, why would you do that to yourself? So I'm a convert.